This is a presentation about multicollinearity and how it affects multiple regression and analysis of covariance, or ANCOVA. So in any of these procedures, what you're trying to do is understand the variability in some variable, which is the dependent or criterion variable, depends on the kind of study, what you would call it. That's represented by this blue circle. So this is all of the sort of ups and downs and whatever it is, whatever phenomenon you're trying to study. This is what you're trying to explain. So when we put in a predictor variable, we can account for some of that. That's the overlap between the two circles. And this is how much variability it could account for. It leaves some over. There's some empty space, that other big piece of the large circle that isn't accounted for, but it is accounting for some of that variability. Now we could also add a second predictor variable trying to account for more of that variability. And this one can account for some piece of it, right there. So you also notice that there's some overlap between them. So they each have a piece that only they are accounting for, each independent variable on its own, and there's a piece that both of them are accounting for that same little part of the variability in the dependent variable, which is that sort of oval shape in the middle. Here's the unique variability for the second predictor we added. That's the part only it can account for. Here's unique variability for the first one that we put in. So they each have their own part, and then this in the middle is the shared variability. So in total, they're able to account for those three segments, but the way we handle the unique variability is going to be different from how we handle the shared variability when it comes to the math of these statistical procedures. And the technical term for this, where they overlap in terms of the part of the dependent variable they're accounting for, is multicollinearity. And this is what's left over, the variability we cannot explain. That's the unexplained, or we call it error variance. Error is just kind of a way of calling it names. It's the part we don't understand yet. So here's our diagram again. And we can look at percentages. So here is the percentage, the part of that large circle that's explained by each variable, is its semi-partial r-squared. That's what percent of the variability in the dv is accounted for by each of the independent variables. So if you look at both of them together, that's the piece they account for. So now notice what happened to the shared variability. It dropped out. We're going to treat that shared variability as though it's error in either ANCOVA or multiple regression. And the reason for that is we're using one of these variables to try and control for something that we're not as interested in. It's a confound that we're trying to take out of the equation. So not including the shared, this is a percent of the total. So those two shaded regions are maybe 30% of the total. So if that part there is 30% of this big circle, then the total r-squared is 30, and let's say the semi-partial r-squared for IV1 is maybe 20, and the semi-partial r-squared for IV2 is 10, 0.10, 10% of the variability accounted for. So here we go again. Each individual variable. If that is 20% of this, then the semi-partial r-squared for that particular variable is 0.20. And so that's telling us not the total amount that it can account for, which would have been the large overlap between the two variables. It's telling you what part of it is the unique variability that only IV1 can account for. And that's really the research question you're usually trying to answer in either ANCOVA or multiple regression. You're trying to find out what is it that just this variable can account for, IV1, after controlling for the effects of IV2. So let's say IV1 is race or ethnicity in a health disparity study. Dependent variable is health. Race or ethnicity accounts for some piece of the total variability after controlling for the effects of some other important variable, like educational level or income. That's why we're treating the shared variability as though it's error. It's because we're trying to kind of weed that out as a competing explanation for the relationship between IV1 and the dependent or criterion variable. And it's done by type 3 sums of squares. That's the mathematical formula. It's sum of squared deviations. So it's how far out is each individual score from its predicted score as error, and how much of that total variability can we actually account for is what goes in the numerator here, the type 3 sums of squares. So it's the explained part, or the signal, compared to the error part, or the noise, and that gives you a semi-partial r squared.